I don't know why that worked, but it worked.
Thanks, man.
Sure.
Okay, so this is sort of an overview of what we're going to talk about. Basically, what oil is, some distinctions between crude oil, refined oils, oil composition, some properties, what happens when it spills, and there will be quizzes. Okay, so this is from a National Academy of Sciences report looking at sources of oil into the marine environment. And one of the things I want to point out here primarily is that natural seeps put a lot of oil in the environment. So that's something to keep in mind because oil is a natural thing and it gets into the water and the environment has some capacity to deal with that. Not huge amounts necessarily, but it does have some capacity. So people sometimes forget that natural seeps are out there and that they're providing oil in the environment and that there's some ability to deal with that. Oil has a bunch of different stuff in it. We'll move on. Oil, as I said, is naturally occurring. It's based on degraded biological material that's been deposited millennia ago and got crushed and has changed chemically over time. It can be in a gas, liquid, or solid forms. Crude oil is composed of thousands of different types of chemicals over varying molecular weights and sizes and complexities, which is one of the reasons why oil, when we talk about oil chemistry and how it's going to behave in the environment, and a lot of that complex mixture feeds into how it's going to behave and what the impacts might be. And of course, because it is a complex mixture, it also is very useful in creating a whole bunch of different types of chemicals and compounds that we use every day, from fertilizers to plastics to so on and so forth. So it's a very versatile, complex mixture of stuff. As the compounds, there's different chemical structures. Depending on the complexity of the chemicals, they're going to have different molecular weights, which are going to behave differently in the environment. A given oil from one field is going to be different from another one because they're going to have different mixtures of those different compounds in different proportions. When we talk about oils, it's generally two broad, I think it is in terms of two broad categories. One is crude oils, and then there's the refined products. And kind of like what I said back here about the different proportions, there you can have variations in oil chemistry across different fields. So like a Saudi Arabian crude is very different from a South Louisiana crude, is very different from a Carpinteria crude, is very different from Alaska North Slope crude because the proportions of the chemical mixtures in there are different. But you can even have differences in the oil chemistry of an oil within the same formation or over time from the same area. So a lot of like the oil chemistry of Alaska North Slope crude has changed dramatically over the last few decades just because it's drawing from different parts of the formation and because they're accessing different areas. So oil chemistry can be very complex in its makeup. So when the oil gets pulled out of the ground, crude oil, it goes to a refinery, gets refined through a fractional distillation process. What they're basically doing is they're essentially boiling the crude oil at different temperatures, and there's a variety of different compounds, as I said, some of which have really low molecular weights. They're very volatile compounds, so they tend to boil off at relatively low temperatures. And so then those are captured, and those may become gasoline, maybe used in gasoline. And they turn up the heat a little more, and they get these slightly heavier weight compounds that can boil off, and those get captured, and those might become diesel or kerosene. And then as you continue that turning up the temperature and boiling off those progressively heavier compounds, the stuff that's left is really heavy. So you can have asphaltenes and some of the much less volatile compounds that are going to be used for other types of products. So it's a way of sort of dividing the crude oil into different fractions, and then those are then used by the general public in different types of fuels, like diesel or jet fuel, for instance, or gasoline. So fractional distillation separates the various components. It's generally characterized by boiling points. The remaining residuum has very high boiling temperatures and a relatively high viscosity typically. And depending on what fraction of oil you're talking about, will, in some ways, determine how it's going to behave in the environment. And we'll talk about that. A whole bunch of stuff that oil's used for. You guys will have a sense of that. Ready? Jim's going to talk about fingerprinting a little bit later today. Part of the complexity of oil is helpful in looking at things, looking at the chemical signature of different oils and being able to distinguish one oil from the other, or seeing which ones are similar, so you can try to trace a source oil to spilled oil on the shoreline. So Jim will talk a little bit about that. And the complexity of the oil, as I said, is going to affect how it behaves in the environment. So your gasolines, which are relatively light molecular weight compounds, are going to tend to have a higher acute toxicity than the heavier compounds, heavier oils, but they're also going to be much less persistent in the environment. So a black oil out in the environment oftentimes will stick around a lot longer than a gasoline, which may just evaporate in a matter of minutes. But the ecological impacts of that black oil may have longer-term consequences, like cancer growth and things like that. And I think Bruce may talk about that tomorrow in his talk about impacts to ecosystems. Whereas the lighter weight compounds like gasoline are going to tend to have a higher acute toxicity issues and kill things quicker, basically. So these are both pictures from Deepwater Horizon. You can see it's the same oil, but it obviously looks and behaves a little bit differently depending on whether it's in the water, it's relatively fresh, or it's on the shoreline as tarballs. We'll talk about that. The complexity in the oil is going to affect how it behaves on the water, how it interacts with shorelines, and the degree to which it penetrates the shorelines. I'll talk about that a little bit. This is a slide from one of our chemists up in Seattle who has a little bit of a dry sense of humor. I think the question is, what's the difference between crude oil and a frozen turkey? And I think the answer is, because I haven't been to the SOS class in a long time, I think the answer is not so much what's in it, but how those elements are arranged. The structural composition of those will determine whether you have crude oil or a frozen turkey. Because they're all natural, right? So oil is composed primarily of hydrocarbons of different structures, and I'll talk about these, primarily the alkanes and the aromatics, just briefly touch on those so you have a general sense, and other speakers will talk about them later in the course. Alkanes are either straight chain or branched, relatively simple hydrocarbons. They have carbon and hydrogen, hence the term hydrocarbons. They can make up a pretty sizable portion of a given container of oil, volume of oil. And these are, because they're relatively simple hydrocarbon chains, they're easily broken down by microbes. So microbes tend to like to eat these before they're going to eat the more complex molecules. And I think Kathleen will talk about that in her talk on Thursday. Aromatic hydrocarbons are a little bit more complicated. They have double bonds between some of the carbons. They can be single rings, like benzene, or they can be fused multi-rings. They can also make up a large proportion of an oil, depending on the oil. And this is the aromatics is where is associated with a lot of the toxicity in oils. The single ring aromatic compounds, oftentimes referred to as BTEXs, benzene, toluene, ethylbenzene, xylenes. That's where a lot of your acute toxicity comes from. That's the type of stuff that volatilizes off pretty quickly. Like if you're pumping gas and you're smelling that gas fume, a lot of that what you're smelling is the volatile organic compounds, or BTEXs. And they can make up a pretty sizable portion of, say, of a light-end refined product like gasoline. Polycyclic aromatic hydrocarbons, which is a multiple fused aromatic rings, those are going to tend to be more associated with your prolonged chronic impacts, like that prompt cancerous growths and tumors and things like that. They're also going to be much more persistent in the environment, just because of the nature of their structure. They're much harder for microbes to break down. And I'll leave it at that. Then there's these polar compounds, which have nitrogen, sulfur, and oxygen, and another reason why they bring this up is because they sometimes affect. They can have, if they're in enough proportion of a given oil, it can really affect how that oil behaves talked about before, gasoline is relatively light molecular weight compounds of that fractional distillation process. They're going to tend to have a lot of the alkanes and aromatics. And you have kerosene and diesel, which are a little bit heavier. They have more carbons in them than gasoline does, so they're heavier molecular weight. And then you have the IFOs, which are much heavier oil products, and they're going to tend to have a lot more of those more complex polycyclic aromatic hydrocarbons. And they may have some of those polar compounds as well, so those types of things are going to affect how it behaves. Talk about physical properties of oil. These are a number of them, but I'm really going to focus on these three. Starting with density. If you're a David Letterman fan, you might think that in terms of will it float? To do a contest and a show about that. When you're talking about density, a lot of people think in terms of specific gravity, which is usually the measure of density used for lots of different hazmat chemicals and things. Where if the specific gravity is less than 1, it will tend to float in fresh water. So fresh water is sort of the baseline situation, and if it's less than 1, if the specific gravity is less than 1, then it's going to tend to float. If it's greater than 1, it's going to tend to sink. The petroleum industry uses an inverse measure of density called API gravity, and there's a conversion formula here, which you know that's not on the quiz, but here the number is greater than 10, then it's going to tend to float. If it's less than 10, then it's going to sink. So until you get used to it, it's kind of hard to, because they're inverse of each other. It takes a little getting used to remembering which one is which. To give you another view of it, fresh water, consider gravity of 1. So if it's less than 1, it's going to float. In fresh water, API gravity of water would be 10. Seawater is a little bit more dense, so it has a higher specific gravity, but a lower API gravity. Most oils are floating oils, so they're going to tend to be less than 1 specific gravity, and they're going to tend to be greater than 10 API gravity. There are some that are particularly heavy, and I'll touch on those a little bit, including this one. This is a spill off Texas coast in November of 2005. It was I think it left the Galveston area with fuel heading to a power plant in Tampa. It hit this is just a few months after Katrina, it hit some submerged platform debris, poked a hole in the bottom of the barge, and the thing started to turn over a period of days. But you do an overflight, and there really wasn't a lot of oil on the surface. But clearly the stability of the barge was affected. It ended up rolling over and turtling. But still, there wasn't all that much oil on the surface. So they started looking at the API gravity of the oil it was carrying, and the majority of the oil was well below 10. So the concern was that the oil, what little oil you saw on the surface, was a small proportion of what was actually released from the barge. It ended up being a 3 million gallon spill, but most of it went straight to the bottom. So in the command post, they set up a little science experiment with a little fish tank with salt water from offshore, and took a composite oil sample from the tanks and squirted it in there, and lo and behold, it went straight to the bottom. And this is a diver video, snapped a screenshot, and it's kind of cool. You watch the divers, they'll wave their hand over the top. It was a really high density, but fairly low viscosity oil, particularly when it's fresh, and you wave their hand over it to kind of break up the little droplets, and then just kind of creepy. Cool from an oil spill science perspective. These are some examples of API gravities for California oils. Some of them are pretty close to 10, so they're not going to float real high in the water, but some of them are relatively high API gravities. But all these are floaters. I think a lot of Coast Guard regulations cluster oils into oil group numbers. There's a poster over here which talks about how those are grouped. It's based on API gravity. So, for instance, the class 1 oil is going to be API gravity greater than 45, but a class 5 oil is going to be API gravity less than 10. So those are group 5 oils that tend to sink. They're inherently dense enough to sink on their own. So if you hear about oil group numbers, Viscosity. So viscosity is a measure of an oil's liquidity or a substance's liquidity. It measures the fluid's resistance to flow. Oil viscosity will decrease with increasing temperatures. So if it's heated up, it's going to get more and more liquid. Like if you heat up a jar of honey or something like that, it's going to get more liquid. As oil weathers and loses those light end compounds, it's going to tend to increase its viscosity. It's going to affect how it behaves in the environment. Obviously, more viscous oil is going to behave a little bit differently than one that can spread out really easily. It's going to affect its ability to penetrate different types of shorelines, like sand shorelines or rocky, cobbly shorelines. And it may affect the different types of response options that are used. Really viscous oils can only be pumped by certain types of pumping equipment, whereas lighter oils, you may have more options. These are some viscosities of some common household items. This is an IFO fuel from Selendang IU in a cobble shoreline. You can see how you can picture an oil like this, if it's relatively fresh and relatively low viscosity, has a really easy time penetrating in between these rather large boulders, cobbles. Whereas the Prestige oil, when it came ashore, it was relatively viscous and the response operation was much different. Its ability to penetrate shorelines is much different and it behaved a lot differently. And the response options are much just because of the viscosity, differences in viscosity. So it can make a big difference as far as how a response unfolds and what type of impacts might be associated. 4 point is kind of related to viscosity. This is actually a temperature when oil will flow. So if the ambient temperature of an oil spill is above the pour point, then the oil is going to behave as a liquid. If it's below the pour point, it's going to behave as a semi-solid, kind of like this, right? So temperature is below the pour point of this oil. And it's a relatively subjective measure. So this is a spill, the Westchester spill in Mississippi River in December of 2000. It was 800,000 gallons of Nigerian crude with a pour point of 45 degrees. At night, it was relatively semi-solid, but then in the warmth of the day, it would heat up and turn to liquid again. So the response options, maybe early in the morning, might be different than late in the afternoon. Also, where the areas it might get to and the types of impacts it might have might change throughout the day because of the difference in temperatures relative to the oil's pour point. Another spill, the Morris J. Berman spill in Puerto Rico in '94, I think it was. That was 750,000 gallons of oil. What happened with this is it was a floating oil. It came into the beaches, picked up sand, and then that sand caused the tarballs to sink in near shore waters. And then in some of the shallow areas, with the heat of the sun, the oil would turn less viscous. The sand particles would drop through the oil, and the oil would basically drip upwards to the surface. So then they put snare off these beaches, and they try to pick up floating oil. So just another example of viscosity in the pour point, which I think, and it's such a cool picture too. It's kind of creepy weird. But, okay. I'll talk about flashpoint briefly, only because it's a safety issue. This is also a temperature that defines the ability, the temperature at which oil vapor can ignite given oil and an ignition source. As it weathers, as an oil weathers, it's going to lose those more volatile compounds, those lighter weight compounds, and its flashpoint is going to increase. So it's going to take more temperature to cause an explosion or a fire. And obviously, it's a big safety issue. This is an incident in June of '99, platform in Louisiana that was evacuated because the pressure gauge was going off scale, and then in a matter of hours, it was a big mess. But at least the people got off safely. They had figured that, but that's part of that has to do with the flashpoint and the oil involved. So we've kind of gone through this fairly quickly already, but now you have a sense of how you have sort of different spectrum of oils with Gasoline being relatively lightweight oil, lower molecular weight compounds, it's going to tend to have a low flash point, so it can ignite and burn at relatively low temperatures, and has a relatively low viscosity. You know, it pours like a liquid relatively easily, whereas diesel is a little bit heavier compounds. It will also have a higher flash point, but its viscosity is similar to gasoline in that it pours relatively easily at room temperatures and ambient temperatures. Intermediate fuel oils are going to have heavier weight compounds. It's going to have a higher flash point than gasoline, certainly. It's going to tend to have a higher viscosity. So it's going to interact differently with different shorelines. Gasoline, diesel shoreline may penetrate sand beaches more easily than IFO, for instance, just because of the virtue of its viscosity. Okay, pop quiz. As temperature decreases, viscosity increases or decreases? Nice. So yeah, you put your jar of honey in the refrigerator, you're dropping the temperature, you're increasing the viscosity, right? What would you expect with an API, an oil with API gravity of 25? Low.
Yeah.
So does that make sense to everybody so far? It's a lot of stuff thrown at you, but lots of pretty pictures, and I know you want to go to lunch, so. So what happens when oil actually hits the water? Right, so there's a number of things that are going to happen. Wishy's going to talk about oil movement. I'm not really going to talk about it too much. I'm going to focus more on spreading and weathering. When an oil hits the water, like a spill like in this exercise we had this morning, oftentimes it's going to come out as one fairly continuous slick of oil. There's going to be wind and wave action that's going to work on it. It's going to spread out a little bit initially, and the wind and waves are going to tear it up into little pieces and into progressively smaller and smaller pieces. So from a continuous slick, it's going to turn into streamers and a more patchy distribution. Then it's going to break up into smaller and smaller bits and tarballs. And so even though it might be a continuous slick at the ship, by the time it gets to the shoreline, it might be scattered tarballs, depending on how far offshore it is, and what kind of oil, what temperatures it is, viscosity, and pour point, all that sort of stuff. But there's that sort of changing progression of how oil is going to be interacting with the environment. So initially, spreading is one of the most important functions in how an oil is moving. It can happen relatively quickly. It has to do with it occurs because of gravity and the oil viscosity. So if you have a really viscous oil, then it's not going to spread as much. So if I take the cup of gasoline on a concrete floor and I pour it, it's going to spread out pretty quickly. Whereas if I took a cup of a heavy fuel oil, it won't spread out quite as far in the same amount of time because it's more viscous, right? So spreading is associated with viscosity of the oil. Speed of spreading is temperature is based on oil type and temperature. So you know about pour point, viscosity, and the relationship between viscosity and temperature. And then it's going to spread out initially, and then it's going to start moving according to wind and currents, like Bush is going to talk about tomorrow. But initially, it's spreading is one of the big movement functions for oil. And then as it's getting broken apart, it's also weathering. So there's all sorts of different mechanisms, weathering mechanisms that oil will undergo. The oil fact sheets in the back of this module kind of talk about how these functions may be different for a diesel fuel and Alaska North Slope crude and an intermediate fuel oil. So you can look at those. But basically, weathering is how you get from a fresh liquid oil to is the things that happen to the oil that cause it to get from a fresh liquid to tarballs and asphalt, much more tackier, drier type conditions. And a lot of it's because of all these different things are happening to the oil out in the environment. So as oil weathers, it becomes less flammable because it's losing those volatile compounds that are evaporating off relatively quickly. It's going to become more viscous because it's losing a lot of those layering compounds and leaving the heavier compounds. It's going to become less smelly because those compounds have volatilized off, right? The ones you can smell. And the acute toxicity is going to decrease because those volatile organic compounds compounds that are associated with the acute toxicity, and the longer chain, heavier compounds are associated with the more chronic toxicity. And each of these weathering mechanisms will have their own sort of time frames. Evaporation, dispersion, dissolution are going to be relatively quick processes in a matter of hours or days, and when you get into things like sedimentation, biodegradation, those can take weeks to months. Evaporation is one of the big removal mechanisms for a surface slick. It's going to be primarily driven by temperature and wind and oil type. This is a screenshot from our ADIOS model, which I think she's going to touch on briefly tomorrow, but neither one of us is really going to show it, like play with it, but you can download it from our website. This gives the volume, in this case of barrels. It gives you time since the oil spill happened. It breaks it down into which proportions are remaining, dispersed, or evaporated. So blue is evaporated. So we're talking about evaporation for this next couple of slides. Focus on the blue portion. So these are 3 different examples of outputs from ADIOS with similar conditions. So 10 knot winds and 1,000 barrels get put in the water. This is a screenshot. Looks out over 5 days. Evaporation, almost all of it is evaporated just within the first 6 hours, certainly within the first day or so. Because it's really lightweight compound, it volatilizes really easily relative to these heavier fuels. Crude oil, depending on the crude oil, they may have a lot of small molecular weight compounds in them. You can have a pretty substantial loss due to evaporation, like in Louisiana crude, that's a fairly light crude. So it has a fairly significant loss based on evaporation, but it's going to drop off over time, so even after the first day or so, your evaporation will essentially stop. And then for a heavier processed fuel or refined product, you may have just a little bit, but you're going to end up with a lot more remaining fuel as time goes on. So we started with originally 1,000 barrels under 10 knot wind conditions. You may end up with 850 barrels left after 5 days, even infinite potentially. So just to kind of build some intuition about how different types of oils and refined products may behave based on their oil chemistry and physical properties. Any questions about that? Fairly straightforward. Okay, dispersion. This is physical dispersion. This is another loss mechanism for surface oil. It's based on the oil type, its viscosity, and the environmental conditions, particularly turbulence, like wave action, for instance. Larger droplets will get torn away from the surface, like based on wave action, and they will tumble in the water column, and if they're large enough, they're going to float back up to the surface and be coalesced into a slick. If the oil droplets are small enough, like between 50 and 70 microns, so like the diameter of a human hair, about that, it's still a floating oil, but it's not a big enough droplet to overcome the inherent turbulence in the system. So droplets that are that small may not rise to the surface very quickly as compared to larger drops. And I'll show you an example in a second. This was a spill in the Northeast. It was a number 2 home heating fuel. It was 828,000 gallons that was released into right near shore, and the surf was 15 to 20 feet high. So a lot of physical dispersion. There really wasn't anything to clean up from a response standpoint, from an oil cleanup standpoint, but because it so thoroughly mixed that diesel-like fuel into the water column, it caused a lot of benthic impacts in the near shore subtidal. So there's a lot of dead things to pick up on the shoreline, but not much oil to pick up, just because of the degree of physical dispersion in the water column. This is an example from Deepwater Horizon. The green line shows maximum wave heights over time. This is April 21st. That's August 1st. There's particular things that happen during the response here. The red is maximum wind speed in the operational area, and the blue is the surface area as determined by satellite imagery, like Judd was talking about earlier. So if you look at how the red line and the blue bars interact, you notice that when the wind is less, the surface area is, as seen by satellite, is much larger. But like what Judd was saying, you can't tell from some of the radar from the synthetic aperture radar imagery, whether or not an area of oil that it sees is thick oil or sheen. What's happening is when the wind lays down, you have those larger droplets are coming up to the surface, and so it looks like there's a larger area of oil, but it may be it may still be very thin oil. So there's a relationship between the physical dispersion that occurs in high wind conditions and the area of oil that's observable. So if you're doing overflights, be cognizant of that, because if you're doing an overflight of an area and you see an area of oil and it's a windy day, and then your admiral does an overflight the next day, and it's not nearly as windy, he may see a much bigger spill. And that's because you've got difference because of the physical dispersion of that oil. So have in the back of your mind, you may need to manage people's expectations a little bit when they dissolution of oil, dissolving the oil in the water column. That is also related to droplet size and the amount of droplets and surface area. But it's not a very big loss mechanism for oil. It's going to depend on the oil. Some of the heavier oils are not going to hardly get lost at all in dissolution, but lighter refined products may. But even gasoline isn't going to really dissolve too much. And remember, usually when you're talking about a marine spill, if you're talking about dissolved oil, you're going to a very large volume of water, so it can dilute pretty quickly. This is an example of dispersed and dissolved oil from Deepwater Horizon from a research cruise that was done in May of 2010. This is water depth. I don't know exactly which location it's being measured at, but it's near the source. This is fluorescence. This black line is fluorescence, so this is indicating the presence of oil, or a layer that's fluorescing like oil will do with their instrumentation. And this red line is dissolved oxygen. So you can see how the dissolved oxygen decreases at a layer at about 1,000 meters, where there's this cloud of microdroplets and dissolved oil, which is what people were tracking with a lot of those research cruises. And this red dashed line is actually a hypoxic threshold. So even though dissolved oxygen concentrations were being depressed by microbes that were consuming those oil particles and dissolved oil fractions, it wasn't depressing it low enough to cause anoxia and problems from a low oxygen condition. So kind of a busy graph, but it's science, man. Cool stuff. Okay, emulsification. So this is sort of, I think of emulsification as almost as the inverse of physical dispersion of oil. This is where you're actually kind of instead of putting oil droplets in the water, you're putting water droplets in the oil. And it can cause change in color of the oil. It can cause increase in volume of that oil, because now you have an oil-water mixture. It can increase the viscosity of that oil, so you may have to have different pumping equipment. Sometimes the volume of that oil-water mixture can be almost all water. It doesn't really take much oil necessarily. If it's a stable emulsion, it can stick around for quite a while. If it's unstable, it can break fairly easily. And one of the things that determines an oil's ability to turn it to emulsify is those polar compounds I talked about earlier, the nitrogen and sulfur oxide compounds. So some of your heavier oils that tend to have a higher proportion of those polar compounds are going to be more likely to emulsify. What the mechanism behind that, I don't know, but you may know, so talk over here. So when you think about stuff in your house that might be an oil and water emulsion, vinaigrette salad dressing is a relatively unstable emulsion. You have to keep shaking it to keep the oil and the vinegar mixed, right, into that sort of frothy consistency. Whereas mayonnaise is a more stable emulsion. You know, it's egg and oil, and it will stay in a fairly viscous form for quite a while, a lot longer than vinaigrette. So just two different examples. And you can see this is a aerial shot of Deepwater Horizon oil, and a close-up shot. You can see how thick and viscous it is. Sedimentation is another removal mechanism, another weathering process. This is, as I said before, most oils float, but when they interact with sediment, sometimes the sediment is enough to cause the oil to sink. So when you spill an oil in a really muddy river like the Mississippi River or in like Cook Inlet, you can almost have the surface oil might actually get kind of eroded from underneath, right? Because these little sand particles and sediment kind of sticks to the oil and the oil drops off. And so we had the PM 932 spill, which is right outside New Orleans, right downtown New Orleans. It, I don't remember how many hundreds of thousands of gallons that was, 280,000, something like that. There was no more surface expression of that oil by the time it got 100 miles downriver to the birds going towards the mountain. Partially because it was interacting with the shorelines and getting stuck to the shore, but also because there's a lot of sediment in the Mississippi River, right? So there's a lot of sedimentation. But it can also happen on shorelines like sandy shorelines. So when oil comes in, like I said, it can pick up sand and it can cause that. The oil can pick up enough sand sometimes to actually sink near shore areas. So sometimes when you have a spill along a sandy beach, one of the things to look for is near shore submerged oil or tarballs, where you may end up having chronic tarballs coming in. We had that for the Dubai Star along the beach in Alameda. It has been a bit of a continuing headache for Deepwater Horizon because of these near shore tar mats that picked up sand and sunk offshore, and then the storm comes through and breaks the oil and brings tarballs to the shoreline. So sedimentation can be a significant thing to think about in our response. Biodegradation is a longer term removal mechanism. There's microbes out there that like oil and like different parts of oil, like eating different compounds. If that weren't the case, then the shoreline of the Gulf of Mexico would have been paved with oil millennia ago just because of all the natural seeps that occur down there. But they're going to tend to go after those simpler hydrocarbons, those straight chain hydrocarbons, those alkanes, and not so they have a much harder time with the multiple ring compounds. So Kathleen's going to talk about that a little bit more later this week. So you have oil and its properties, and it gets filled in the water. It spreads out. It gets mixed with you experience a lot of turbulence from winds and waves. That continuous slick gets broken up into smaller and smaller pieces into tarballs, and then it becomes harder and harder to see from the air and the boats, but it still ends up on shorelines. So kind of, again, managing expectations when people are doing overflights, for instance. You may not be able to see a lot of oil offshore if it's broken up into tarballs, but people may still be getting tarballs in their shoreline. The public may be reporting it. Local agencies might be particularly concerned about particularly high amenity beaches, the heavily recreational used beaches. But you fly over an area and you won't really see it very much. So just keep in mind that the small tarballs can still prompt a response, but may be hard to track when you're doing overflights or doing larger area monitoring of some sort. But because they're relatively heavily weathered oil, they can persist for quite a while because they've lost a lot of those light end compounds. And as Bushy might talk about later on when he talks about transport mechanisms, tarballs can travel a long distance. In central and northern California in the wintertime, it's not uncommon for tarballs that have leaked out of natural seeps in Southern California to move all the way up the coast and come ashore in Half Moon Bay or Monterey or something like that. And they're oftentimes going to be heavily weathered, but they've traveled a long, long distance just because of the wind and currents that are pushing them around. So, but no one really notices them until they show up on the beach and they're walking their dog and their dog's feet get all oily and This is just a screenshot of our ADIOS model, which is our oil weathering model. You can download that from our website and play with it. I think it's a nice tool to kind of build some intuition about oil types and how they behave differently under different conditions. So you can kind of play with some of those variables and kind of get a better sense of how big your problem is. If you had 1,000 gallons of diesel spill on 10 miles offshore, is it going to make it to shore? Kind of questions. But I'm not going to play with it here. Okay, so we talked about different API levels. High API fuels are your lighter end fuels, gasoline, diesel fuel, for instance. They're going to have a higher acute toxicity, like I said before. They're going to be low viscosity, so they can spread out really quickly into really thin sheens that may be sub-micron level, so thinner than a sheet of than a layer of paint. And they're going to be lighter end products, so they're going to evaporate pretty quickly, so they're not going to be as persistent. Whereas you get down to low API fuels, they're going to be black, they're going to be more viscous, they're not going to spread out as much, they're going to be more likely to create tarballs, they're going to be more persistent, they're not going to be as have as high acute toxicity, but may have a more persistent toxicity over time. So you kind of get a better sense of what the spectrum of oils are that are behaving out there. So when you see it out in the field, you may have relatively fresh oil. This series of pictures is from the Salandang IU out in Alaska. So it's a really kind of shiny black liquid with some iridescence. It looks like a relatively fresh oil to me. And then as time went on, it got more and more weathered. It's not as shiny anymore. It's more viscous. It's actually sticking on rock walls opposed to puddles in the ground. This little drip here, this shiny drip, is because the sun had been beating on it for a while, so it decreased the viscosity, and that kind of dripped out a little bit. But otherwise, it's relatively dull sheen to it. Interacts with sediments and becomes. You can kind of get a sense that it's becoming more and more of a persistent oil as it goes through this weathering. It's becoming more viscous. Maybe it's becoming less toxic. So you get to this point where it's sitting on rocks and you can't hardly scrape it off with your fingernail. So it's probably not presenting a lot of risk to wildlife, but it's still persisting. And chemically it's very different than it was back here in its properties in this chemistry. Okay, other concepts. The initial stage of the spill, what is it done in process? Moving what? Moving oil. Nice. Okay, dominant weather process or removal of gasoline. Questions?